Okay. Well, first off, you see we're getting pretty close to the end of the semester. We have all of April and the first week of May pretty much left. So about 4 or 5 weeks left. And these are all the sections we have left. My goal is to try to get finished before the end of April. So I'll give you guys a couple of weeks to catch up all the work, do all your tests, and get ready to take your final exam. With that, for example, I mean, some of these, like Newton's method, that'll take us some time, not because it's difficult, but because it's what's called an iterative process. Is we don't get the answer right off the bat. We have to do the process 5, 10, 15 times until we get too close to a number, and that's our solution. So some may take more time than others, but the rest of these, like signal notations, that's going to take us some time as well. But the rest of these, we should do 2 per class without stress at all. I won't try to stress you out. We have just enough to do 1 per day, finish up at the end of the semester. But I want to give you guys time at the end of the semester to finish up all your work. All right, so let's begin. Indeterminate forms. Indeterminate, what does that mean? Basically, it simply means cannot be determined. In mathematics, there are certain types. In other words, for example, fractions. That looks like a number, but we don't know what it is. Is it 1? Is it 0? Is it undefined? Is it infinity? We don't know. Or another one. Infinity over infinity. What is that? So these look like numbers, and even we have exponential ones. A to the power infinity. So we're going to look at functions that have these type of exponents. Basically, we're looking at both extremes, going to 0 or going to infinity. That's the two functions. So whenever we have equations like that, for example, the example we have on our sheet, f of x equals 3x minus sine x over x. From chapter 1, when we first learned about chapter 1, chapter 2, when we first learned about the limit theorem, we don't take limits at easy numbers. What would be the limit number you'd go on this equation? What number x would look like the most difficult, would give us a problem? Yeah. So what we would look at is, what is the limit as x approaches 0 of this function? What's the first thing you do when you get an equation like this? When you get a limit equation, what's the first thing you do? Plug it in. This is the value x, we're plugging it in. So let's see what happens. Three times 0 is 0. What's sine of 0? 0. So we got an indeterminate form of 0 over 0. So we're thinking that the first derivative doesn't exist there because we can't take the limit of it. Remember, we'd use the Riemann sums to figure out what is exactly is a derivative. So what this says is, no, it's not really define that yet. So we said at zero, we have nothing. We can't get to zero. But using what we call L'Hopital's rule, it's named after a person named, was it Guillaume? Guillaume de L'Hopital, a French mathematician, philosopher, physicist, who thought that, hey, if we have an indeterminate form of an equation, 0 over 0, infinity over infinity, we can go further. If it's 0 over 0, what do we learn in the first week of class? If it's 0 over 0, then there may be something we can do algebraically that we can manipulate the equation, because obviously they have something in common. So something should be able to factor out. He thought that. So that's pretty cool. Let's do that. Let's look at it. But then he came up with a better idea. If you have an equation that becomes indeterminate when you first do it, if it's 0 over 0 or infinity over infinity, then take the derivatives of both the top and the bottom separately, not the quotient rule. These are derivatives of top and bottom separately. You keep on doing that until one of the top of the bottom is no longer 0. In other words, at this first one, we have 0 over 0. So we take a derivative of it. What's the derivative of the top number going to be? This is a separate equation. What's the derivative of 3x? So we have the limit of 3. What's the derivative of sine x? Cosine x. What's the derivative of x? 1. We see in the bottom, it's no longer a 0 when we go to a, or we go to 0. So we stop doing the L'Hopital's rule, and let's just plug it in there. What's cosine of 0? 1. So 3 minus 1 is 2 over 1. So the limit of this function is 2. That's how L'Hopital's rule works. Let's see what our examples are. Again, you keep on doing it until one or both of the functions are no longer 0. Yes. You could take it up to infinity derivatives until something occurs. That's until the top or the bottom or the bottom is no longer 0 when you plug in your limit point. So there's no telling how many times you take the derivative of it. For example, the radical, the square root. If we had a radical on the bottom and a trig function on top, there are no finishes. They keep on increasing in size. So let's look at example 1 in our sheet. A. The limit as x approaches 0. We just did that one actually. 3x minus sine x over x. The first step when we use L'Hopital's rule, the top equation is our f of x, and the bottom equation is our g of x. So the first thing you do, remember, this is the way we read this is x goes to a, whatever that number is. Again, you have to remember what we did in chapter 1 and chapter 2 to do the rest of this stuff. So when I say plug a, well, a is whatever this limit value is. Plug that into top and bottom, see what happens. So that's what we did. We had 3 times 0 sine of 0 over 0. That gives us 0 over 0. If we get 0 over 0 or infinity over infinity, then we can use L'Hopital's rule. Again, L'Hopital's rule is if that gives us 0 over 0 or infinity over infinity, we take the derivative of the top and the bottom separately and try it again. You keep on doing it until one of them or both of them are no longer zeros when you plug in a. So in this one, the derivative of the top is 3 minus cosine x over 1. So we'll plug in 0. 3 cosine of 0 over 1. 3 minus 1 over 1. And that's our limit. The limit as x approaches 0 of square root of 1 plus x minus 1 over x. So what's your first step? Plug it in. We got 0 over 0. Since we get 0 over 0, what do? Take the derivative of the top and the derivative of the bottom. So this, remember, the square root of x plus 1 plus x is the same thing as 1 plus x to the power 1/2. The derivative of that, we have to use a chain rule, which is what? The derivative of the outside and subtract 1 times the derivative of the inside. So that's the derivative of this first term. We got the derivative of 1 is 0. The derivative of x is 1. I see a lot of people staring at the board like they've never seen this stuff before. Plug in 0. 1 plus 0 minus 0 over 1 doesn't matter that. So it's 1 over 2 radical 1 over 2 times 1. It's 1/2. That's our limit. Now we have the third one, C. The limit as x approaches 0 of radical at 1 plus x minus 1 minus x over 2 over x squared. Actually, I want you guys to do this. So the first thing we do is plug in our 0. 1 plus 0 minus 1, 0 over 2, 0 squared. 1 plus 0 is 1. 0 over 2 is 0. So 1 minus 1 over 0 is 0 over 0. So we can use L'Hopital's rule. So the first thing we do is take the derivative of top and bottom. The derivative of the bottom is 2x. Radical is this. So we bring down the outer exponent, subtract 1, times the derivative of the inside, which is just 1. So the derivative of this derivative of 1 is 0. The derivative of x over 2 is 1 over 2. Because the derivative of x is 1, so it's 1 over 2. Now plug in 0. 1 plus 0 minus 1/2 over 2 times 0. So it's 1/2 minus 1/2 over 0. We got to do it again. To answer your question earlier, so do we take it again? Yeah, we take it until we need to. So now we're only using this equation. So the derivative of 1 over 2 radical 1 plus x is 1/2 1 plus x to the power negative 1/2. Power comes down, and we subtract 1, which makes it negative 3/2 times the inside. So it's negative 1 over 4. So negative 1 over 4, 1 plus 0 to the 3/2 minus 0. Derivative of 2x is 2. So this becomes the limit as x approaches. Take the top fraction, multiply by the flip of the bottom, which gives us negative 1 over 4. This is x. So -1, 4 times 2 is 8. Plug in 0, so it becomes -1, 8, 1 plus 0 to 3 halves. -1 over 8. 1 plus 0 is 1. To any power is 1. So the answer is -1/8. Now, if you're copying this, there's a lot of work to do. This is chapter 1, chapter 2 stuff. You got to practice your homework. Because this is Mickey Mouse to where we're going. I know you guys can do it, or else you wouldn't be in this room. I have faith in y'all. Let's look at D. The limit as x approaches it. Okay, how do we know that we couldn't go any further? Because when we took the derivative of 2x, what do we get? 2. Since that's no longer can no longer be 0, that's as far as whatever's going to happen now at this point is the answer. If it's 0 over 2, the answer is 0. Or whatever the answer is, the answer is. But once one of the top or the bottom is no longer it's no longer a non-zero limit, you're done. It's just it is what it is. X minus sine x over x cubed. So the first thing, let's put 0 in there. So 0 is 0, sine of 0 is 0. So we take L'Hopital's. The derivative of x is 1. Derivative of sine is cosine. The derivative of x cubed is 3x squared. Plug 0 in there again. We get 1. Cosine of 0 is 1. 3 times 0 is 0. We do it again. Derivative of 1 is 0. Derivative of cosine is negative sine. Derivative of 3x squared is 6x. So that becomes a positive. So plug it in there. We have sine of 0, 6 times 0. Sine of 0 is 0, 6 times. We got it again. One more time. Because now we look at the derivative of sine is cosine. Derivative of 6x is 6. Cosine at 0 over 6. 1/6. Now, how did you get undefined or 0? Oh, you factored it out, but you couldn't factor it out. But your second choice was okay. That's why I give everybody 3 tries at tests. Good job. Everybody else get that? Can I get it? Good. All right, let's look at example 2. When I took calculus 1 many years, L'Hopital's rule was my favorite topic of all the topics we discussed, simply because it's so simple, straightforward. Okay, let's use this one. The limit as x approaches 0 of 1 minus cosine x over x plus x squared. One cosine of 0, 0 plus 0 squared, 1 minus 1 over 0, so we get 0 over 0. The derivative of 1 is 0. The derivative of cosine is negative sine. Derivative of x is 1 plus 2x. So that becomes a plus. So we get the limit as x approaches 0 of sine x over 1 plus 2x. So far, so good? Now we plug in 0. Sine of 0 is 0. 1 plus 2 times 0 is 0. That's the answer. It's easy to be tempted to go one step further. That's where you got 1/2. Because remember, you take the derivatives until you reach a point where you have a non-zero derivative. And when x goes to 0, this 1 stays there. So we're done taking derivatives. It is what it is. The answer is 0. All that work for nothing. Okay, let's get some more practice under our belt. The limit as x approaches 0 from the right of sine x over x squared. What this show, these A and B, the next two examples, well, I'll put B right here. Limit as x approaches 0 from the left of sine x over x squared. What this goes to show you is you can take one-sided limits also and use L'Hopital's rule. There's not much moving parts here. So let's see what happens here. Secant at pi over 2 is 1 over cosine pi over 2. It's 1 over 0, which is infinity. Tangent at pi over 2 is sine over cosine. It's also infinity, so it's infinity over infinity. So we take a derivative. Derivative of secant is secant tangent. Derivative of 1 is 0. Derivative of tangent is secant squared. Secants cancel. Tangent is, oops, secant is 1 over cosine. Tangent is sine over cosine, which makes it infinity. One of the secants cancel. Tangent is sine over cosine, secant's 1 over cosine. Take the top, leave it alone. Flip the bottom. Cosines cancel, so we just have sine. At pi over 2, sine of pi over 2 is 1. Now we're doing this one. All right, let's look at this. As x goes to infinity, ln x, ln and infinity, what does the graph of ln look like? So as x goes to infinity, this one goes to infinity. So we have infinity. Square root of infinity is infinity, so infinity over infinity. So we take the derivative. The derivative of ln x is what? 1 over x. The square root of x is x to the power 1/2, which is 1/2 x to the power negative 1/2 times the derivative of the inside. So it's 1 over 2 radical x. 1 over 2 radical x times 2, the 2's cancel. Because that coefficient there is there. Let's fix that up. So we have the top, flip the bottom. Square root of x divided by x is what? What's that? Well, first off, x is the same thing as the square root of x squared, right? So what we have here is square root of x over the square root of x squared. One of these cancels. So we have 1 over the square root of x. Or you could do it with the exponents, which is x to the power 1/2 over x to the power 1. 1 minus 1/2 is 1/2. You could have done that. So as x goes to infinity, 1 over infinity is what? As the bottom gets larger, the number gets smaller. So it goes to 0. So this one, the answer is 0. How many do I put infinity or undefined there? No, because as the x on the bottom gets larger, the number, the fraction gets smaller and smaller and smaller. It looks like this. It's a decreasing function. So you can see. The limit as x approaches infinity of e to the x over x squared. So let's see. E to the infinity over infinity squared is infinity over infinity. Yes. So we can use L'Hopital's rule. What's the derivative of e to the x? E to the x. It's EU du. So, but the derivative of x is 1, so that's it. What's the derivative of x squared? 2x. So we have e to the infinity over 2 times infinity. It's still going to give us infinity over infinity. Why is e to the power infinity infinity? What does the graph look like? It's an exponential function. As x goes to infinity, the graph goes to infinity. So we got to do it again. So this doesn't get us anywhere. So we take it again. Derivative of e to the x is e to the x. The derivative of 2x is 2. Now this is as far as we can go because that's a non-zero derivative. E to the infinity over 2 equals what? Half of infinity is still infinity. Oh, you were just waiting to see what the final answer is going to be? What did you think it was going to be? I know it's tough because infinity divided by 2. It's still going to be infinity. That's a very common. Because now, what do I do here? So, okay, so those were examples of infinity over infinity. Now we have 2 more. The case here is infinity times 0 and infinity minus infinity. That's the case here. Let's think about it. Infinity times 0, what do you think it is? It's okay. What do you think infinity minus infinity? Okay. Infinity, are all infinities the same size? They only be zeros if they're exactly the same. And we don't know what they are because so even the difference could be infinity. So that's you see why these are indeterminate. We can't say much about them. Let's look at example 5. We're looking at this form first. So a, the limit as x approaches infinity of x sine 1 over x. Now, do you see how it fits this condition? So if we plug in x, so we have infinity sine 1 over infinity. 1 over infinity is what? 0. Sine of 0, 0. So it matches that form. Because of that, we can use L'Hopital's rule. Okay, you see the problem of taking the derivative of sine 1 over h or 1 over x, because then you have to use the chain rule. So we'll have cosine 1 over x times 1 over x, the derivative of 1 over x, which is negative 1 over x squared. But then we keep on going. And then, so we use substitution. We're not used to seeing this. So let's say that h is equal to 1 over x. So we have sine of h. So what is x going to be? If we solve for x, what do we get? Because this is, if we flip them, x is 1 over h. Now, why did I do that? So now we have what does that equal? Because yeah, taking a derivative of a rational angle usually not too much fun. So take the derivative of it and see what we have there. So we just use this transformation, or substitution, I should say. Yes.
So we don't use
Yep. Oh, you can use substitution anytime you want to, if it makes life easier for you. Actually, we strongly suggest using substitution for larger equations or more complex equations, because we would be using the chain rule over and over and over and over and never stop. Let's look at B. Right, we got this? Because I'm saying that I'm substituting that h is 1 over x. And then now I got to figure out what x is. Because that becomes h. What is x with reference to h? Well, actually, then, since I'm going to h, I should have also had this. But once we get to this form, and we're going to infinity, that's all that matters. All right, so let's look at the next one. 5b. The limit as x approaches 0 from the right of radical x ln x. Okay, here's a question. Why in this one do I only look at one side limits? Yeah, because radicals, first off, the graph of a radical looks like this. The graph of an ln looks like this. I cannot use negative x's. Or I cannot use 0 because 0 doesn't exist in ln. So all my x's have to be greater than 0. So take it from there. It's not going to take us too many places because our first derivative, this one's going to be negative 1 over 2 radical x. This one's going to be 1 over x. So it's just going to take us nowhere, really. There is a property here. If we have this pattern, we can change it using algebraic or trigonometric manipulations. So becomes we can convert it from infinity times zero to one over or infinity over infinity. Infinity over infinity is a lot easier for us to work with because then the derivatives are much easier. So how would we convert this? Because if we plug in zero inside there, we get so square root of zero is what? Zero. Square as x goes to zero, what does ln zero become? Because as it gets closer to zero, it goes down to negative infinity. So that's why we're in this form. How can we convert it to this? Well, we can't do anything with the ln x. That's pretty much stationary. What can we do with this? Is there another way we can write it? This equation can be written as it's the same thing, isn't it? Because this is over one. If I put it on the bottom, I reciprocate it. Now we're going to infinity over infinity. You're thinking. If you look at this, so we have A on top and B over C on the bottom. So it's A over 1 times the flip. So we have AC over B. Well, B was 1, so we just have AC. Now this becomes ln at 0, 1 over radical 0. This goes to infinity. This goes to infinity. So we use L'Hopital's rule. The derivative of ln x is 1 over x. The derivative of 1 over radical x is the same thing as negative 1/2 x to the negative 3/2, which makes it negative 1 over 2 x to the power 3/2. So it becomes negative 1 over 2 x to the 3/2. Yeah, then what you may say is 1 over 0, 1 over 0 is still infinity over infinity. But again, algebraically, what do we do? Take the top fraction, we have the limit of it, I should say. So take the top fraction, flip the bottom, which makes it negative 2 x to the 3/2 over 1. So we have negative 2. 3/2 over 1 becomes what? with x to the power 3/2 over x to the power 1, which is 2 over 2. That becomes, subtract the exponents, so it becomes x to the power 1/2 negative 2 squared root of x. So what we're looking at here, as x goes to 0 from the right, we're looking at negative 2 radical x. So it's going to stay negative, but when this goes to 0, and there's your answer. Yes, it's easy if you know what to do next. This is one of the reasons, another major reason why I don't give a zillion homework problems, because that way you'll have time just to try out new things. And that's it. You have all of algebra and all of trig to rely back on. What can you do? How can you manipulate it? I'm not saying it's easy. It just takes practice. And once you start seeing these patterns, it gets pretty easy. Is there a C? No. Example 6. This is of the form infinity minus infinity. The limit as x approaches 0 of 1 over sine x. So you see how this is, what is sine of 0? Sine of 0 is what? 1 over 0 is infinity. 1 over 0 is infinity. So it's 0 minus infinity. Because it has that case, we can use L'Hopital's rule. We take the derivative of both of these separately and see what we get. So go ahead. The first way we're going to look at this is we're using the property of the limit of a minus b is the same thing as the limit of a minus the limit of b. So we can look at the limit of 1 over sine x as x goes to 0 minus the limit of 1 over x as x goes to 0. So it goes 1 over sine of 0, which is infinity, 1 over 0, which is infinity. So it's 0, infinity minus infinity, which is this case. So because of that, we can use L'Hopital's rule. The derivative of 1 is 0. The derivative of sine x the derivative of 1 is 0. The derivative of x is 1. When x goes to 0, we get 0 over 1 minus 0 over 1, which is 0. Pretty straightforward. Now, what would the other way be? The other way is combining these two. Get a least common denominator. So the second way, let me see what that equation was. Which one was that? Oh, 1 over sine. So looking at this, this equation needs an x over x. This one needs a sine over sine. So what we have is x minus sine x over x sine x. We combine these two into one equation. If we put in 0, 0 minus 0, 0 times 0, so it's 0 over 0, we can use L'Hopital's rule. So in the numerator, the derivative of x is what? Derivative of sine, cosine. Now on the bottom, we have to use the product rule. X sine x, the derivative of x is 1, derivative of that is cosine. So we get sine x plus x cosine x. Plug in 0, so we get 1 minus 1, 0 plus 0. L'Hopital's again. Derivative of 1 is 0. Cosine is negative sine. Derivative of sine x is cosine x. Now we do the product rule again. So we have x cosine x, 1 negative sine. So it's going to be cosine x minus x sine x. Which makes it positive sine x. That's 2 cosine x minus x sine x. Plug in 0. 0, 2 times 1 minus 0. Same thing. Which way was easier? The first way was easier. By using the properties. Again, anytime you can use the properties, go ahead. Which example is that? Make sense? Again, it's not that easily drawn out. It's a lot of work, but it gives us an answer. Yes.
I still don't understand why it's 0. Why wouldn't it be 1 for the cosine minus 1 over 1? It's also equal to 0.
In which part? Here? Oh, the first, this one here? Because 0 over cosine is 0. I don't care what the bottom is, it's 0. Minus 0 is 0. That's derivative of a constant. Remember, when you do L'Hopital's rule, is you treat this is one function, this is another function. You treat them both separately. So the derivative of 1 is 0. The derivative of sine x is cosine x. This is not one equation anymore. We use L'Hopital's. We're now looking at two separate functions and treat them both independent of each other. Yes.
So it's 1/0 versus 0/1, is it still zero?
No. 1/0 is infinity. 0/1 is 0. Just ask yourself this. How many times can 1 fit into 0? It can't. 0 times. How many times can nothing fit into 1? Infinite times. Like the example I use in class is, how many ways can I give you nothing for Christmas? Let me count the ways forever. So now that does it with the 0/0, infinity over infinity, 0 times infinity, or 0 minus infinity minus infinity. Now we're looking for indeterminate powers. On your look at your sheets under indeterminate powers. What it says there is pretty important. Limits that lead to the form 1 to the power infinity, 0 to the power 0, and infinity to the power 0 can sometimes be handled by taking the logarithm and then exponentiating the solution to get the answer. We use L'Hopital's rule to find the limit of the logarithm expression and then exponentiate the result to find the original function limit. This procedure is justified by the continuity of exponential functions. So we'll be using this property. If the limit of x approaches a of f of x equals the limit, then the limit as x approaches a of f of x is equal to the limit of e to the ln of f of x, which is equal to the e power l. If the limit of the function is L, then the limit, remember, E and ln cancel each other out. These two are the same things. But we know the limit of the f of n function is L. So the limit ln of L is just L. That's what we're going to be using in this last set. Example 7. You have this on your sheet I gave you all. And that's the reason I printed it out for you. You don't have to copy everything down. Example 7. Apply L'Hopital's rule to show the limit as x approaches 0 from the right of 1 plus x 1 over x is equal to e. So what's f of x? F of x is this function part. So we define that, and we have to find the limit as x approaches 0 from the right of ln of f of x according to this. So what do we know? Let's look at this. So ln of f of x is equal to what? Is the ln f of x is this function here. So what does that become? Using the rules of ln that we know so far, what can we do here? Bring the exponent to the front. Very good. So the limit of this function, we're trying to find this. So the limit of as x approaches 0 from the right gives us the limit 1 plus x over x. Can we use L'Hopital's rule here? Why? Is that the only condition? Are you sure the top 0? Why?
LN1.
Very good. Because what we have here, if we plug in 0, we have 1 plus 0 over 0. ln of 1 over 0. ln of 1 is 0. Because at 1, the y value is 0, right? So we can take L'Hopital's rule. The top, what's the derivative of ln 1 plus x? If you don't remember, ln u, the derivative is du over u. So the u is 1 plus x. What's the derivative of 1 plus x? 1. That goes on top. And the bottom is the 1 plus x. And the derivative of x is 1. So this becomes as x goes to 0, we get 1 over 1, which is 1. That's our answer. Well, that's our answer so far. Because what does this find us? What does that define for us? The limit of this. That's not the answer of the question. Look at your sheet. What is the question looking for? We're asked to show that the limit of this is equal to e. Go back to the rule. Limit of f of x is limit of e to the ln f of x. Didn't we just find the limit of f of x? Which is what? So we know the limit as x approaches 0 from the right of our original function, 1 plus x 1 over x, is equal to the limit as x approaches 0 of our function, which is equal to, according to that sheet, limit as x approaches 0 from the right of e ln f of x. And this part is what we just found there. So it's e to the 1, which makes it e. That's what we're trying to prove. So this is an example of, we have to first find the exponent before we plug it back into the equation. Because in this transformation, we know what a function is here. Now this function, take the ln of it, and we find the limit of it, and that's what we just did. Let's look at the same thing pretty much on example 8. Find the limit as x approaches infinity of x to the power 1 over x. Does this satisfy one of our conditions for the indeterminate powers? Is it 1 to the power infinity, 0 to the power 0, or infinity to the power 0? Yeah, as x goes to infinity, we got infinity, 1 over infinity, which is infinity to the power 0. So how do we solve this? What's our f of x? This is our f of x right here. So we need to find the limit as x goes to infinity of ln f of x. Why do we have to find that? Why do we found our function, so we need to find the limit of ln f of x. Why? Let's look at our formula. The limit of our function becomes limit of e to the power ln f of x. Once we find this, we just plug it into the power of e, and that's our limit. That's what we have to look for. So what we have to do here is we take the limit as x approaches infinity of ln f of x. So that becomes the limit of x as x goes to infinity of our function x to the power 1 over x. Because that's what. So again, as we did earlier, the rules of ln, if you don't remember them, review your rules of logarithms. You can't have an exponent. So this exponent comes in front of the whole thing, actually, the whole limit. So it's 1 over x, ln x. So that becomes ln x over x. So we set it up first. Now what do we do? Plug it in to see what we get. Ln at infinity is what? Infinity over infinity. Because remember, the graph of ln looks like this. As x goes to infinity, this one goes to infinity. So we have infinity over infinity. What does that tell us? Why is that important? We can use L'Hopital's. So we take the limit as x approaches infinity, the derivative of ln x, 1 over x, very good. Derivative of x. So we have the limit as x approaches infinity of 1 over x, which becomes 0. Are we done? No, because this is our exponent to our e. So therefore, we had the limit as x approaches infinity of our function, which becomes the limit of our function, which is the limit of e to the power ln f of x. So we get e to the power 0, which is 1. That's our final answer. Do we have anything else? Remember the mean value theorem? What's the mean value theorem? What's the formula for it? The mean value theorem is what? What does it find for us? The mean value theorem. Those are critical values. What's that?
That there is a point where the tangent line is parallel to the secant line.
Right. Now, what does that mean? So if we had a curve that looks like this, we have 2 points at A and at B. The slope of the secant line and there's a point somewhere between A and B where the tangent line has the same slope. These are equal. Now, that's pictorially what they mean. What does it mean mathematically? This is defined by a derivative at some point C. This is algebraic. I should make this G. That's the mean value theorem. It says that the slope of a secant line between in a closed interval, there's a point C within that closed interval where the tangent of that curve is parallel to that secant line. That's the mean value theorem. Now we have a theorem 7 is Cauchy's theorem. What he's saying with respect to what we just talked about, the L'Hopital's rule, what he's saying is instead of just one function, we're now going to deal with the derivative of two functions at a single point. If you think about this, what Cauchy just proved, because now we have two separate lines. If we follow the mean value theorem, that equals f of b minus f of a over b minus a, right? And then we have another function. It follows its slope. If we divide these two, like we did in L'Hopital's rule, then we get this fraction divided by this fraction. What's the rule about fraction over a fraction? What do? Take the top fraction, leave it alone. And multiply by the flip of the bottom. So these two cancel, which leaves us that. This shows to us why L'Hopital's rule can work. We use that as a proof because if I can take the derivative of both of them, that means they have to have the slopes have to be equal or have to have something in common, and they do, the endpoints. So now with that, we can now this is the reason why we can take the derivative of both separately. We'd have to do the quotient rule. All right, that's it for today. There aren't any more examples. I was hoping to get to section 6 because that's where we start dealing with applications. Section 6 is optimization, application optimization problems. But we'll do that next time.